Okay, so today we're diving into the story of how AI actually learned to remember. It's this awesome tale of a brilliant breakthrough, but also a tragic flaw, and the super clever solutions that came along and changed, well, everything. Let's kick things off with a question that really gets to the core of a massive challenge in AI. You know when you're typing a text and your phone just knows how to finish your sentence? How does it do that? Seriously, how does it have any clue what you're going to say next? Well, the answer lies in tackling this one fundamental problem. Traditional AI has no memory. Seriously, think about it. Those classic neural networks, kind of the workhorses of AI, they treat every single piece of information like it's a totally brand new event. Everything is independent. That means they literally have no concept of the past. But that's not how our world works at all, is it? I mean, so much of what we understand relies completely on sequence and context, right? The meaning of a sentence totally changes depending on the order of the words. And the direction of the stock market? Well, that obviously depends on the prices that came right before it. So, all this stuff, text, stock prices, audio, this is what we call sequential data. And to make any sense of it, a model has to grasp this idea of, well, temporal dependence. Fancy term, but it just means it needs to remember what happened a second ago to have any shot at predicting what's coming next. All right, so let's get into the good stuff. This is where our first hero steps onto the scene, the recurrent neural network, or RNN for short. And this thing was designed for one specific reason, to tackle this exact problem of memory. Now, the absolute genius of the RNN is its core idea, this concept of recurrence. What it does is it uses a loop that passes information from one step of the network to the very next one, basically creating a chain of memory. Yeah, you can totally think of this loop as the RNN's own internal memory. It's sometimes called its hidden state. And what this means is that the output at any given moment doesn't just depend on what it's seeing right now, but on everything it has seen before. For the first time, an AI had a sense of history. Okay, so check this out. A really cool way to visualize this loop is to just unfold it over time. When you do that, you see this chain-like structure. And each link in that chain is processing a new piece of data, but it's also getting information from the link that came right before it. It's like a memory conveyor belt. But, of course, here's the twist in the story. This super elegant solution, this beautiful, simple loop of memory, it had a critical flaw. An almost fatal one, actually. Yeah, it turns out the RNN's memory was shockingly short-term. It was great at remembering what happened a few steps back, but anything, and I mean anything, further in the past just, poof, faded away. This is a famous problem. It's called the vanishing gradient problem. And the best way to think about it is like that game of telephone, right? Where a message gets passed down a long line of people. As the network tries to learn by sending a signal way back through its own history, that signal gets weaker and more garbled with every single step. And after a while, the original message is just gone. It's completely lost. And that makes it impossible to connect events from the distant past to what's happening now. So you can see the problem, right? The AI community desperately needed a new hero, or as it turns out, two heroes, to come in and solve this memory crisis and finally give AI a true, long-lasting memory. First up, we have the LSTM, which stands for long short-term memory. Now, this is a much more complex version of an RNN cell, and it introduced this brilliant idea of gates. Think of these gates like little valves or even bouncers at a club. They give the network the power to decide exactly what new info to let in and store, what old useless info to kick out and forget, and what to actually use for the final output. Super clever. And then, right on its heels, came the GRU, or Gated Recurrent Unit. This one is like a streamlined, faster version of the LSTM. It gets you pretty much the same awesome results, but with a much simpler design. It basically combined a couple of the gates, which made it way more efficient, and honestly, because of that, it's often the go-to choice in the real world. Okay, so this chart here really lays out the trade-offs perfectly. You've got the original RNN, which was fast, but, well, it had the memory of a goldfish. Then the LSTM and the GRU come along and solve that memory problem, which is amazing, but it came at a cost. They were slower and way more complex to train. So when you're picking between them, it really boils down to this key trade-off. The LSTM, it gives you more knobs to turn, more complexity for finer control over its memory, and that can be perfect for certain really tricky tasks. But the GRU, It's just so much more efficient and faster to get up and running, which makes it a fantastic starting point for almost any project. Okay, but let's fast forward to the modern day, to the AI world of today, because this story does not end here. You might be thinking, is this the final chapter for our RNN heroes? Well, just a few years ago, a completely new architecture showed up and just changed the game. I mean, completely, especially for understanding language. It's called the transformer. And yeah, it has pretty much replaced RNNs from almost every major language task out there. And here's why. And by the way, this is a super hot topic in tech interviews. Transformers have this massive advantage. Their design lets them look at all parts of a sentence at the same time, not one word after another. This makes them incredibly fast to train. Plus, they use this cool mechanism called attention, which lets them weigh the importance of different words, giving them an even crazier grasp of context and long-term dependencies. And that's not an exaggeration. In fact, today, get this, it's estimated that over 95% of all the state-of-the-art models for natural language processing, we're talking about the big ones like ChatGPT, Google's Gemini, they are all based on the transformer architecture. So, that brings us to the big question, right? If transformers are so totally dominant, why did we just spend all this time learning about the humble little RNN? Is it just obsolete, a relic of AI history? No, not at all. The RNN absolutely still has a vital role to play. Think about it. For all those times you have limited computing power, like on your phone or on tiny little Internet of Things devices, the lightweight, efficient nature of an RNN is perfect. It's a game changer. And maybe just as important, you can't really understand the evolution of modern AI without understanding the journey of the RNN. And that kind of leaves us with one final thought to chew on. In this world of giant, massive transformers, is there still a place for that simple, elegant loop? As these AI models get bigger and bigger, is it possible that the clever, efficient solutions of the past